Okay, welcome back, class. And today we're going to start the last chapter, and chapter 12 on statistics. And so in section 1, we're going to talk about sampling, frequency distributions, and graphs. Now, we're going to talk about how to describe the population whose properties are being analyzed, select an appropriate sampling technique, how to organize and present the data, and identify deceptions in visual displays. Okay, now statistics. So the branch of statistics, or the science of statistics, is the science of collecting, organizing, analyzing, and interpreting data, as well as drawing conclusions based on the data. Okay, and so we're drawing conclusions about a population based on the data that we collect on the population. Now, there are two branches of statistics that we're going to talk about: descriptive statistics and inferential statistics. Descriptive statistics is the actual collecting, organizing, summarizing, and the presentation of data. That's where we do our calculations and such. Okay, so that is the one branch. Now, the other branch, inferential statistics, is where we make our generalizations to the population. We draw conclusions about our population that we're studying. Whatever the characteristic that we're studying, we're going to then draw conclusions about the whole population based on the sample data. Now, a population is very simple. It's all of the objects that we're studying. It's the collection of everything, everyone that we're studying. So that is considered the population. Okay. So if we're talking about heights of women, then we don't specify it any more than that, then the population that we're interested in is all women. Okay. So a sample is a subset of the population, meaning that, okay, if I randomly select 500 women, then that is going to be my sample, because it's not all women, it's a subset of women. So that's going to be a sample. Representative sample means that a sample that exhibits the same characteristics as that, or similar characteristics as that of the target population that we're trying to study. Okay, so a representative sample basically has the same characteristics, the same makeup as what we see in the entire population. So then if that's the case, we have a representative sample. Now, if we look at this example here, so here we have a group of hotel owners, right? And they want, in a large city, and they decide to conduct a survey among citizens of the city to discover their opinions about casino gambling. Now, in this case here, the population under study then is, what do they want? They want opinions. Well, whose opinions? Citizens of the city. So the population that they're targeting, that they want to know more about, is citizens of the city. Now, one of the hotel owners suggests, hey, why don't we survey all people at 6 of the largest nightclubs in the city on a Saturday night. Let's go out one Saturday night, and we'll go to the 6 largest nightclubs, and we'll ask all the people there what they think about casino gambling. Does that seem like a good idea? No, it's a terrible idea. The nightclub people, the population, all the people that go to the nightclubs on a Saturday night are not going to be representative of all of the city's citizens. So it would not be a representative sample. So that would not be a good idea. So how do we get a representative sample? Well, we want a random sample. If we have a random sample, then we know that chances are very high that we are going to get a sample that is representative. In fact, that's one of the ways to guarantee that we have a representative sample, is to do a random sampling method. So a random sample is a sample obtained in such a way that every element in the population has an equal chance. There's that keyword, equal chance of being selected for the sample. So here's the methodology. We identify each element in the population, or that could be subject or person, what have you. We assign numbers to each element in the population. Then we randomly select a subset of numbers. And then we assign the elements in the population who have those numbers, and those become our sample set. Okay. Now this is a particular type of sampling method called simple random sampling method. Okay. Now, which of the following is the best way to select a random sample to find out how the city citizens feel about casino gambling? So 1A, we randomly survey people who live in the oceanfront condominiums in the city. Well, what do you think about that one? Well, the problem is that many hotels lie along the oceanfront, and these people might object to the increased traffic and noise which may result. It also does not give each citizen of the city an equal chance, right? Because the people who don't live on the oceanfront do not have a chance of being in the sample. B, survey the first 200 people whose names appear in the city's telephone directory. Now, this does not give each citizen an equal chance either, okay? Because you're just taking the first 200 people, which means the people that have A's, B's, and C's are going to be much more likely to be chosen than people who have X, Y, and Z as their last name. Randomly select neighborhoods of the city and then randomly survey people within the selected neighborhoods. That is a great idea. Okay, that is a good sampling method because each citizen has an equal chance because you're randomly selecting a neighborhood. So each neighborhood has an equal chance of being selected. Therefore, everybody has an equal chance because if your neighborhood is randomly selected, then everybody in that city is surveyed. So this is a good random sampling method. Now, this is not simple random sampling method. This is actually called cluster sampling, which we'll talk about later. Now, constructing a frequency distribution. So a frequency distribution is just a table that involves all of the possible values in the sample and the frequencies of each observed value. In other words, how many times does a particular value show up in the data set? Okay, that's the frequency. Okay, so if we take these 35 boys, right, and we want to find the age, right? So we want a data of the age of maximum yearly growth of 35 boys. So at what age did they grow the most during that year? And so here are all the ages where they grew the most. And so here's the data. So what we do is we list all of the values that show up in the data. So all the values that show up, or even the ones that don't show up. So we take the minimum value and the maximum value and list all of the values in between. Okay? And then we put the frequencies of how many times each value showed up. And this now is a distribution. This is a frequency distribution. It's a table that has the X values and it has a table of frequencies. And that's it. So if I ask you to construct a frequency distribution, this is it right here. Okay. Now you don't have to have the total here, but it's important to sum this total up because if you have 35 numbers here, you definitely better have the frequencies add up to the sample size. Now, what are some of the conclusions that we can draw from this example? Well, let's look at it. Well, we see that the majority of boys, not the majority, but the largest frequency of boys happened at 14. So it seems like the growth spurt happens around age 14 for the most part. Or if you look at the range here, 13 to 15. So if you look at 13 to 15, how many boys fall into the age group 13 to 15? Well, you've got 22. So that the majority of boys basically have their growth spurt somewhere between 13 and 15 based on this data. Okay, and so again, maximum growth for most subjects occurred between the ages of 12 and 15, so they said 12 and 15, which is fine. The number of boys who attain their maximum yearly growth at a given age increases until age 14 and then decreases after that. So notice that it goes up, 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 and then it hits a peak, then it goes down, down, down. Okay, so that's also an interesting feature to be aware of. So now, here are the statistics scores for a class of 40 students. Okay, so we want to group the frequencies. So this is for grouped data. So now notice that in this example here, what's the range of the data? We go from 10 to 18, so it has a small range. When it comes to a small range, we don't want to group the data. Okay, so this would be an ungrouped frequency distribution. Okay, now if we have a large range of data, for example, what's the minimum value in here? It looks like the minimum value is 45, or no, 43. Okay, anything smaller? No, I don't see any. So 43 is the smallest value. What's the largest value that we have here? Is it 94? Do we see anything bigger than 94? I don't think so. I think 94 is the largest. So if we subtract 94 and we subtract 43 from 94, what do we get? We get 51. Well, that's a huge range. I do not want to list 51 scores in a table. That would be too big. So in this case here, we're going to group them into classes. So this is where we're going to create a grouped frequency distribution. So notice the difference. If we have a small range of values, ungrouped. If we have a large range of values, group them. Okay? How do you know when to group and when not to group? Usually anything much larger than 10, then we're going to want to group. But I will usually let you know which to do. Okay? So now, first thing we need to do is we need to figure out the frequency, the classes we want. Okay? Now, since letter grades are given by a 10-point range, let's use that for our classes. Okay, now this typically isn't the way we do it, but in this context, it's fine. So let's do 40 to 49, 50 to 59, 60 to 69, 70 to 79, 80 to 89, and 90 to 99. Now notice that the class widths are 10. Okay, so the class width, how do we determine the class width? By subtracting the lower class limit. So this is the lower class limit of a class. This is the upper class limit. Notice that there's no overlap between classes. We don't want any overlap. So notice also that going from 40 to 50 is 10. Going from 50 to 60 is 10. So the class width is 10. We don't go across this. We don't subtract here. This would be wrong. It's one class limit to the next class limit. So if we go from one lower class limit to the next lower class limit, or we could go from one upper class limit to the next upper class limit, you'll get the same answer. So we can see that the class width is 10. So how many classes do we end up with in this case? We end up with what? 1, 2, 3, 4, 5, 6. Now, what about 100 though? See, we should have 100 here. Okay, but we want to make sure all our classes are of the same size, same class width. Okay, that's one of the distincting features that we want to make sure we have when we're talking about grouped frequency distributions. All of the classes must have the same class width. Okay, so now, in this case here, since there were no hundreds, it doesn't matter for our purposes, but in real life, you're probably going to want to include 100 in there. But in this case, again, it's irrelevant. So now that we have our classes, now all we have to do is figure out the frequencies. So what do? We figure out, here's our class range for the first class, and we count how many of these numbers fall from 40 to 49. And we just count. So 47 does. Okay, so we look for anything in the 40s. That's the easiest way to do it. Anything in the 40s. There's 3. And so there's 3. And then we go to the 50s, right? Anything in the 50s, right? So we count anything that has a 5. So we got 1, 2, 3, 4, 5. So then we keep doing this and we come up with, oops, did I miss one? Did I miss one? Hold on. 1, 2, 3, 4, 5. I did. 6. I missed that one. Okay, and so when we do this, now we have our grouped frequency distribution. Here are our classes. Notice the lower class limits and the upper class limits, and notice that the differences between these is 10, and the differences between these is 10. Okay, and so again, add up the frequencies, and you should get 40, which is exactly the number of scores that we have. Okay, let's see here. This here is used in some cases where the number could be extraordinarily high. And usually if we're talking about money, ranges of income or salaries or things like that, it could be, so we usually go, okay, we have our classes and the last class will be greater than some amount, or the first class will be less than some amount. Okay, so the first and last class could be larger, but typically we want them to be the same width. Now, histograms. Histograms are created by using grouped data. So we're going to use a grouped frequency distribution, but then what we're going to do is we're going to connect these rectangles. Okay. Now, this is an example of a ungrouped frequency histogram. Okay, because there are no classes, so each bar represents one number. Okay, and notice that the bars are touching. So a histogram, the bars are always touching. So it's basically, in this case, you could look at it as a bar chart where the bars are touching. Okay, now in a grouped frequency distribution, you're going to use what's called class boundaries, and the class boundaries are basically the midpoint between the class limits. And so if we go back to this example, notice that there's a gap from 49 to 50. So in order to create a histogram, we would take these class limits and we would connect them by taking the midpoint, the halfway point between 49 and 50, which is 49 and a half. And then the halfway point between 59 and 60 is 59 and a half. So notice that it's always the same 10, right? So the boundary for this one would be 49 and a half, 59 and a half, 69 and a half, 79 and a half, 89 and a half, and then your upper class boundary would be 99 and a half, and your lower class boundary would be 39 and a half. And so that's how you would do this with grouped distributions. But in this case here, it's ungrouped, so you just make sure the bars touch and all the numbers are centered. Okay, so this is the first data set that we're talking about. So this is an example of a histogram. Okay, now a frequency polygon. Now again, ignore the histogram here. Okay, forget the histogram. Pretend the histogram is not there, because that's not in a frequency polygon. But it is there to illustrate one thing, that the way you construct a frequency polygon is by using the midpoints of each class. Okay, so in this case it doesn't matter because the midpoint is right at the number, because this is ungrouped frequency. If it was a grouped frequency where you had a class, then you would use the class midpoint. So it would be at the midpoint, and then the height is basically the dot is put right at the height of the bar. Okay, so you put the midpoint dot at where the frequency is at. Okay, and so what you do is you end up with a series of dots where the dots are located at the midpoint on the x-axis, and then the y-axis is just the frequency. And you just put the dot at the height, the appropriate height. And then once you have all the dots plotted on your graph, then all you do is connect the dots with a straight line. Not a curved line, a straight line. Now, the one thing also that I need to mention is the graph touches the x-axis. How do you make the graph touch the x-axis? Do you just willy-nilly arbitrarily draw a line till it hits the x-axis? No. The way you do it is you add a class to the left side and to the right side. So what you would do is you would subtract 1 in this case, so you'd put 1 at 9, and you'd make another class at 19, and you just make those frequencies 0. Okay. If it's a grouped frequency table or a grouped frequency polygon that you're using, then you would just use the midpoint and you would subtract off the class width to get to the next midpoint here and the upper midpoint up here and do the same thing. You just make the frequency 0. Okay, so now stem and leaf plots. Okay, so this is an example of a stem and leaf diagram or stem and leaf plots. These are not very oftenly used in real life. I've never seen it done, but again, because for this class and for the completeness of understanding, you are going to have to know how to construct these, and they're very easy. So there's 2 parts to constructing a stem and leaf plots: the stem and the leaves. The stem consists of the tens digits or the hundreds digits if it does go to the hundreds. The leaves consist of the units digits, or it could be a decimal digit if you're dealing with a decimal. But again, it just depends on how it's constructed. Now, so in this case, for the exam scores, let's create a stem and leaf diagram for these exam scores. So what we're going to do is we're going to treat all of the ones digits as leaves, and then all of the tens digits are going to be treated as the stem. Okay, so we go through and we look at all of the tens digits. So what's the minimum tens digit? Well, it's going to be in the 40s. What's the maximum? It's going to be in the 90s. So we're going to draw a stem that goes from 40, so 4, to 9. And then we're going to attach the leaves to each of the stem numbers in increasing order. So what would that look like? So it would look like this. Okay. So here are the first thing. So we're going to enter in the data items in the first row. Okay, so here's the 4, 5, 6, 7, 8, 9. So here are the stem values, okay? And here are the leaves. So this is just the items in the first row. Now, if you take all of the data, then you're going to get this stem and leaf diagram. Notice how now we've got all 40 numbers listed, okay? So you should be able to count all of these units, and it's going to add up to 40. Also, you have the data in your display. So you've got 4 and 7. So you know this means 47. 4 and 5 equals 45. 5 and 6 equals 56. Now, one of the things you're going to want to have on your plot, on your leaf and stem and leaf diagram, is a key that tells your audience or the reader what these numbers mean. Because if I look at this set and there's no key, then I'm not sure if these numbers here mean 47 or 4.7. Maybe it's talking about distribution of baby weights. And this could mean 4.7 pounds. And this could mean 7.5 pounds. Okay, so you have to give your audience a key. And basically it looks something like this. It'll say 4 and then a vertical line, 3 equals 43. And so this would be the key. So now everybody knows that, hey, 4/7 equals 47, 8/4 equals 84, and so on. Okay, and then of course you're always going to want a title to let your audience know what this data represents and things like that. So now, okay, So now here are the last topic, deceptions of visual display. So one of the things that you have to be careful is the scale that's being used. Okay, so this is U.S. poverty rate rapidly increasing. So if you look at this graph, it looks like, oh my gosh, the poverty rate in the United States rapidly increased between 2001 to 2004, and it grew up huge. Okay, but you see this break in the graph here. It's not starting at zero. So you got to be careful, because if you don't start at zero, you could get extreme increases or decreases. Okay, so here, in all three of these graphs, they're presenting the same data. But look at in this graph compared to this graph. Okay, what's the difference? Different scales. Okay, now the break in the graph is okay. Now I'm not saying anything about the break in the graph, but be careful when you're looking at things that have a break, because they're deleting part of the graph. Now that's okay. That's okay, as long as it doesn't change the scale of the graph. Now here, notice the scale here. This is going up by what? 11.3, 11.7, 11.1. This is going up by a larger increment. Okay, so here, this shows from 11 to 13, so over the years, this shows a increasing slowly. This graph shows that, oh my gosh, it's increasing rapidly. What's the difference? This is, you're zooming in. This is a closer view, a zoomed in view, than this one. This is more of a you're zooming out. Okay, and then here's a table, right? So here's the table, and you're looking at the poverty rates: 12.6, 12.7, 12.5, 12.1, and 11.7. So if you look at this table, it doesn't look like they're increasing very fast if you look at the numbers. Okay, in fact, you're looking at from 5 years, from 2001 to 2005, you're looking at a total increase of less than 1% over a 5-year period. Okay, so graphs can be used to distort the underlying data. So a lot of times you're not going to have this data. You're going to have graphs. Looking at the data is one thing, but a lot of times you're going to want to use graphs. Graphs are very easy to read, very easy to understand, and they're very useful, but they have to be used appropriately. So the graph on the left stretches the scale on the vertical axis to create the impression of a rapidly increasing poverty rate. The graph on the right compresses the scale on the vertical axis to create the impression of a slowly increasing poverty rate. So both of these graphs distort in one way or another. Okay. So things to watch for in visual displays of data. 1, is there a title that explains what's being displayed? Very important to have a title. If you don't have a title, people won't understand what it is that your graph is talking about. And in the case of quizzes and exams, if I ask you to create a graph and you don't put a title on, you're going to lose some points, right? So it's very important to have a title. Are numbers lined up with the tick marks on the vertical axis that clearly indicate the scale? Has the scale been varied to create a more or less dramatic impression than shown by the actual data? Okay, so careful of that. Do too many design and cosmetic effects draw attention from or distort the data? So again, too much bells and whistles on the graph. Okay, has the wrong impression been created about how the data are changing because equally spaced time intervals are not used on the horizontal axis? So that's used a lot when you're talking about time series data. So you have time on the x-axis. You always want to use the same time increment, because if there's different time increments, you can definitely distort and send the wrong message to your readers. Okay. Furthermore, has a time interval been chosen that allows the data to be interpreted in various ways? So is it confusing to the reader what is being shown? Can I interpret? Is there more than one way to interpret the data based on your graph? So it brings ambiguity into the interpretation. 5, are the bar sizes scaled proportionately in terms of the data they represent? That's a big one, right? So you want the bars to be have equal widths, equally spaced, and you want the height of the bar to be proportional to the amount of data that the bar represents, right? 6, is there a source that indicates where the data display came from, right? So you always want to make sure that you put a source of the data somewhere around the graph so that the reader can go and look up the data for themselves if they want to, okay? If you just give a graph and it has no source of where the data came from to make that graph, it could have been just created out of thin air from somebody who just wanted to get their point across and get their agenda out there with no real data. So if there's no source, you basically can just ignore the graph because you have no idea if it's reliable or not. Okay, so in my work and whenever I read articles or I'm reading anything that somebody throws a graph together and there's no source, I'll ask for a source. And if they can't give me a source, I basically just ignore it because there's no reason to believe it if there's no source, because I'm going to want to look at the data and I'm going to want to go research it myself, right? As any intelligent, critical thinking person would do, right? I'm not just going to take somebody's word for something if they say something, and neither should you. Okay, cosmetic effects. So here's a great example of cosmetic effects that really distort and confuse what in the world they're trying to say. Okay, so here, this is the home with equal heights, but different frontal additions and shadow lengths. Okay, so it makes it impossible to tell if they are proportionately depict the given areas. So this is a great example of where you have no idea. Does this shadow really proportionately depict the increase in the dwelling? Okay, it's hard to tell. It's very hard to tell. Okay, so from here, does this mean, it seems like from here to here, it's like more than doubled. And then from here to here, it looks like it more than doubled. So did the size of houses double? Right? So this is the number of square feet. So did the average square feet for a single family home double from 1980 to 1990? Did it double then from 1990 to 2010? I don't know. Plus, oh, look at here. 1980 to 1990, that's a 10-year gap. And then here, from 1990 to 2010, that's a 20-year gap. So now, the data indicate that this is not the case. There was a greater increase in the area from 1980 through 1990, averaging 34 square feet per year, than from 1990 to 2010. So interesting. Okay, interesting. So that it says time intervals on the horizontal are not uniform in size, so making it appear that the dwelling swelling has been linear, which it has not. But also, if you look at the data, this is not the case. It says there was a greater increase in area from 1980 to 1990 than from 1990 to 2010. Okay, so this definitely sends the wrong message, and people will definitely get the wrong, draw the wrong conclusion based on this graph. So you want to avoid any what we call pictographs. Any graph that uses pictures like this or any kind of pictograph, avoid them like the plague. They're pretty, but they're bad. Okay, so that's the end of this section. Again, if you have any questions, please email me. Be ready to learn. Again, please, 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 please email me or email me through Blackboard, and let me know what you think and what your questions are, where you're getting confused, what you don't understand, and we'll talk about it in class, and we'll do more of this stuff in class. Okay? Don't just rely on these PowerPoints and the videos. Bring your questions to class, work on the suggested homework, and practice using the examples in the textbook as well. Do whatever you can to review and practice this stuff, and then whatever you get stuck on or whatever questions you have, let me know. Bring them up in class so we can tackle them together. And until then, have a great day. That's okay. This is what we do. That's just I think